One day, in the not-too-distant future, robots will travel to the far reaches of the universe.
All systems activate. Systems prepare for disembarkation.
They will be the first to colonize new worlds. Robots will lead the way in the exploration of deep space.
Activate.
Are robots the future of mankind? Robots, machines of our nightmares, or servants of man? In the 1930s film Metropolis, the robot was an evil character. It represented our darkest fears.
If we're not careful, it may indeed be the case that early generations of superintelligent robots will simply eliminate us, as a nuisance, basically having better things to do with the space and the matter we're occupying.
He's a robot. Without you, what could he do?
There's no limit to what he could do. He could destroy the Earth.
And by the 1950s, they had become even more sinister and powerful. But over the last few decades, our opinions of robots have dramatically changed. They've been reinvented as the police force of the future.
He's really good.
He's not a guy, he's a machine.
But can real robots match the exploits of their celluloid cousins?
Although it looks really good that robots can, on TV, like lift up a building and throw Captain Kirk across the room, in real life, robots are fragile, weak machines which don't have the energy to do anything more than barely move themselves around.
While the movies were creating ruthless men of steel, real robots were starting their own painful march into the world. Robots are still basic, but over the last few decades, they have advanced enormously. Before robots can become the masters of the universe, or even the servants of mankind, they need to accomplish one important thing. They need to move around.
Locomotion in general, of course, is very important because a robot that can't transport itself around is a very inefficient sort of thing.
Without mobility, a robot is limited only to where it can reach. And so the mobility as a function is the crux. It is the essential capability for complex achievement.
Getting around isn't easy. The simplest method is to use wheels, but they can be defeated by uneven terrain or stairs. Even tracks will eventually fail. All sorts of ingenious modes of locomotion have been tried. The best solution is to build a robot with legs.
I think that in a practical sense, walking is absolutely critical to the incorporation of robots into everyday life. We have built our world for legged creatures, namely ourselves. And so any robot that is going to move around in that world in an efficient way and in a relatively quick way is going to have to traverse terrain that we have built for ourselves. Things like stairs, and of course, since we have legs, it makes sense to have the robots have legs also.
To find out the best way for a robot to move around, the scientists looked to nature.
Nature basically slithers, walks, and swims, and flies. So I think that's the future of robotics.
because nature has already done a lot of the work and tried out a lot of the possibilities. And so it makes sense to take advantage of whatever lessons nature has already figured out.
Nature is sort of the ultimate engineer, you know. It's had time to play around with all the different ideas, and it's picked the ones that really work the best.
There have been many attempts to copy nature, some successful, others less than perfect. Some robots have gone where even nature didn't dare go. The first question that needs to be answered is, how many legs should a robot have?
Is 2 legs better than 4? And we say, well, you know, ostriches are really fast, they run on 2 legs, but the fact is the fastest animal is a cheetah, and it has 4 legs.
The first 6-legged walking insect robots were created in the 1980s at MIT. These evolved into Genghis. It walks like an insect, always keeping enough legs on the ground at any one time so it doesn't fall over. Hermes is more advanced. The legs have been programmed to move in different patterns so it can walk with different gaits. Cricket was made from model airplane parts. It moves its 6 legs in a simple gait using just 3 motors. The robot Ariel is based on the crab. This mine-clearing robot walks sideways. It is designed to operate in shallow water and can still walk, even if flipped over on its back. Designed at Carnegie Mellon University, Ambler is a massive 6-legged robot. At 20 feet high, it's the largest walking robot ever built. But because it only moves 1 leg at a time, it's pretty slow. The adaptive suspension machine is also modeled on an insect. This human-driven robot uses 6 legs and can walk sideways as well as forward. It is designed as a truck that could climb over terrain impossible for a wheeled vehicle. One of the most revolutionary 6-legged robots ever made is Odex-1. Built in 1983 by Steve Bartholet, it was years ahead of its time. The robot gets around by moving 3 legs at a time and maintains its balance by keeping the other 3 legs firmly on the ground. This is known as static balance.
A static leg system is one that when he stops, or for that matter, when he's in motion, he always has at least 3 feet on the ground at one time with the center of gravity somewhere within that pattern. So he doesn't have to actively balance himself. He's always stable. And when he comes to a stop, he's just as stable as a 3-legged stool because he's got at least 3 feet on the ground, arrayed in a pattern. The center of gravity is safely toward the center of it.
Odex uses the same technique to climb stairs. But 6-legged robots have a major disadvantage. 6 legs requires 6 motors, which increases the robot's weight and power requirements. This is a problem that nature has already overcome.
Once you're larger than a mouse, those extra legs are redundant. They're a waste. They're more energy and power than you actually need. Mother Nature knew this. You'll never find a creature in nature larger than an ounce with more than 4 legs.
4-legged robots are lighter and more energy efficient, but they're more unstable.
With quadrupeds, the issue is somewhat more complicated. You still need to figure out how to get from point A to point B, but you have to do so in a manner that doesn't get your legs tied up or cause an instability to occur.
The solution is to move 1 leg at a time, keeping the other 3 on the ground. But these robots are painfully slow. Is it possible for a robot to walk with just 2 legs?
I like robots that have 2 legs, and the advantage there is that if you're going to have more than 2 limbs, you can use the other 2 limbs as arms.
2 for me is good because 2 legs is half of 4 legs, so I only have to make half as many legs, which is a factor. I mean, cost goes down, if you only have to build 2 as opposed to 4 legs. And it makes the robot smaller and lighter. So there are some engineering advantages to making 2 legs.
The major disadvantage is that balance is much more difficult. So you are now, if you have 2 legs, during a great part of the walking cycle, you're really only on 1, and you have to achieve balance with that. And so the robot has to have mechanisms to balance which are different than what you would have with 6 legs. With 6 legs, you can just stop at any point and you are statically balanced. With 2 legs, you have to do dynamic balance.
Dynamic balance was developed by Mark Raybert, who founded the MIT Leg Laboratory in the 1980s. He started with 1-legged robots.
In our lab, we've been concentrating on active balance. And to do that, initially, we built machines that only had 1 leg. A 1-legged machine has to balance because it doesn't have any opportunity for static support. That is, you can't spread out the feet in order to keep it balanced passively. So we built 1-legged machines. They actually hop instead of walk. And we found that the control of these machines wasn't really too difficult.
The robot had sensors which measured its motion and had a computer brain which used this information to reposition the leg between hops. Mark Raybert then moved on to 2-legged robots. The computer calculated where the leg should move to keep it balanced. All Raybert's dynamic robots had to keep moving to stay on their feet. His dynamic robots performed amazing feats. This robot is Spring Flamingo. It doesn't need to keep hopping or jumping to stop itself from falling over. It walks by feel. Sensors in its ankles tell it how to angle its feet to maintain balance. Spring Flamingo was developed by Gil Pratt, the present chief of the Leg Laboratory.
Most robots built to date have really incorporated their vision systems or their navigation systems very tightly into the control loop for locomotion. And what we're trying to do with our robot is very similar to the way that a hiker in the woods tends to walk, which is that the hiker doesn't look at his or her toes all the time, but rather just sort of trusts their feet to do the right thing.
Spring Flamingo uses another idea borrowed from nature: tendons. The motors are located above the legs, and power is transferred down wire tendons.
In animals, you find that the same thing happens. Any fast animal, you find that the ankles of the animal tend to be very graceful and very lightweight, and there's really just bone and tendon there, and all the muscle is pushed up as far into the leg, as far up towards the body of the animal as possible. This allows the leg to move as quickly as possible, to accelerate very fast, and thus less power has to be used in order to move the legs of the robot.
This robot copies another brilliant idea from nature: muscles.
If you want something that moves backwards and forwards, whether it's a finger or an arm or a leg, taking motors which are spinning fast and gearing them down and starting them and stopping them and so on is very difficult.
Richard Greenhill has developed robotic muscles. They work by pumping compressed air into a rubber sheath surrounded by a wire outer mesh. As the rubber sheath expands, the mesh contracts and moves the limb.
So we've now got a muscle that behaves remarkably similarly to a human muscle. It contracts about the same amount, similar speed, similar power. And the thing about it is that it's very natural and easy then to connect it to a hand, to an elbow, to an arm, and you get the same movement as a human.
This robot not only copies human muscles, it has 2 legs and is designed to walk upright.
The reason for following the human design is it's a design that's been tried and tested. It's been through a hole that nature can throw at it for millions of years. It is the best design. Why should we sit down and invent something if we can just borrow from this brilliant and wonderful thing? So if we want to build a robot, what better? Of course, the problem is, can we? And that's the challenge.
It's extremely difficult. Even though we take walking for granted, it's something humans take years to master. Keeping upright and not falling over is more difficult than it first appears. Early humanoid robots tried to keep their balance by rocking from side to side or using a counterweight. This robot walks more like a human, but it still needs its student helpers to stop it from falling over. But there is one robot that makes all the others look like beginners. This is the Honda Robot P3, the most advanced robot in the world. It has taken over 20 years to develop at a cost of over $100 million. There were numerous prototypes which slowly learned to replicate human walking. The Honda P3 walks by moving its weight from one leg to the other. Using sensors in the ankles, knees, and hips, and a sophisticated vision system, it can actually walk up and down stairs. This is the latest version of the P3. Slightly smaller and lighter, it can walk much faster. It is so good, it looks almost like a man in a robot suit. It can easily walk up and down any steps. The tether is only in case it falls. But just walking is not enough to be a true humanoid. A robot needs hands. Fingers and thumbs allow the robot to touch, grasp, and perform complex tasks. The first robotic hands were simple, crude devices for grabbing and holding. They became more sophisticated as industrial robots took on more and more complex jobs. But they were still unable to perform intricate maneuvers. The breakthrough came when roboticists were able to copy our own hands. The human hand's a masterpiece of engineering. It uses tendons to transmit power to the fingers down muscles in the forearms. This robotic hand uses the same system.
The reason tendons are used in biological systems as well as robot systems is because it allows you to place the actuator at a distance from the place where work is being done.
By situating the actuators, or motors which power the tendons, at the base of the arm, the fingers can be thin and dexterous. The hand is controlled by rope tendons, which bend or extend the fingers. The hand can grasp and make fine movements just like a human hand, and it can do them with precision and without ever tiring. The ultimate machine intelligence was HAL.
Discovery 1 voyages towards Jupiter. Controlling the mission is a talking computer known as HAL.
Hal, you're the brain and central nervous system of the ship. Does this ever cause you any lack of confidence?
Let me put it this way, Mr. Raymer. No 9,000 computer has ever made a mistake or distorted information.
HAL was conceived by Arthur C. Clarke, the famous science fiction writer.
Probably before the end of this century, we will be able to construct computers or artificial intelligences which can go out on their own and develop lines of thought irrespective of any programming, and which may, in principle, be more intelligent than we are.
Machines as intelligent as HAL have yet to appear. We already have robots that can move around, but we need them to become more intelligent.
Mobility is the thing that sets the stage for the evolution of intelligence, because it creates novel conditions for an organism to deal with, simply by bringing the organism from one place to another in the wide and surprising world.
Humans learn by moving and experiencing new stimuli. This could also be the key to developing robotic intelligence. Roboticists argued robots would be able to learn movement as easily as humans.
In the 1960s, when computer-controlled robotics started, it was believed that interacting with the world would be a fairly minor problem.
Hans Moravec found that writing a computer program for a robot to navigate across a room was more difficult than first thought.
It turned out, though, that moving across a room was far harder than proving geometry theorems. After 9 years of working on this problem, I finally, in 1979, ended up with a program that could sometimes pick its way across a cluttered room. This whole process only worked about 3 times out of 4. The other time out of 4, it would become confused about where it was, or it would fail to see an obstacle and would either run into a silly place or simply bump into something.
Vision recognition systems require a powerful computer. To identify an obstacle and then maneuver around it takes a huge number of calculations. And if an object is moved, the robot becomes easily confused. The revolution in microchip technology greatly enhanced the way that robots work. Tasks that once took minutes could be achieved in a fraction of a second. These advances have allowed robots like Xavier to move freely, knowing where to go and how to get there. It can visually identify and avoid obstacles and stop when it has finished its task.
Xavier here. I just stopped to say hi.
But there is more to intelligence than just navigation and obstacle avoidance. A robot must be able to think if it is to function in the real world. For survival, a robot must be able to deal with an infinite number of possible situations. If a robot brain were programmed with every single possibility, it would have a nervous breakdown trying to cope with all the information. The alternative is not to program the robot with all eventualities, but to program it how to learn. As children grow up, they learn to perform simple tasks by trial and error. As they mature, their brains allow them to learn abstract rules and concepts. They not only know how to move the chess pieces, but where to move them. They learn that if they make a bad move, they'll lose the game. These experimental robots also learn by trial and error. They have the equivalent of 50 brain cells compared to our billions, enough to learn not to bump into the walls of their enclosure. A sensor tells them when they are getting close to the wall. They learn to control their wheels when detecting the wall so that they rarely hit it. This humanoid robot, Cog, is also a learning robot. But it's far more complex and learns by watching human behavior.
This is our robot Cog. It's got eyes up here which should respond to motion right now. It's looking to see when something moves, and then it tries to reach out to it. So when it first started, it didn't really know how to look at motion, and it didn't really know how to reach for that motion, but over time it's learnt those two things. Much as a human child, an infant, learns over the first few weeks of life how to coordinate its eyes with what it sees, and then how to coordinate its stubby little arms and reach out towards things. The single most surprising thing that happened with this robot was one day Cynthia Farrell was playing with the robot, trying to demonstrate that the arms were moving, and we were videotaping it. And afterwards, when we looked at that videotape, we said, oh, the robot and Cynthia are taking turns doing something. But our plan wasn't to put turn-taking into the robot for quite a while.
Cog was learning to behave just like a child with his parent. But this level of sophistication takes immense computing power and years of programming. Now, some roboticists believe that even this self-learning approach will reach a limit and require too much computer power. They believe this will stop the robot from evolving into the machine of our dreams.
The complexity barrier is one that I've seen happen with a variety of robotics projects, and it is essentially an absolute killer. It basically starts when a roboticist has a wonderful idea of, I want to build a robot. And he has a wonderful 3-week period where he actually builds the frame and builds the thing that carries the computer. And then it might be as much as 2 man-years of programming just to get the robot to actually do anything at all. And when they finally get it to do something, if they want to make it do something a little bit more, oh, it walks across the carpet, but now can we get it to go up a step? All of a sudden now they need twice as much power and twice as much programming. The whole trick then is, how do we overcome this complexity barrier?
Mark Tilden's solution is a radical new concept. His robots don't use digital computers for brains. They use simple analog transistors, an idea inspired by nature.
We have to recognize, for example, that out of 20 million species on this planet, not one of them uses a computer for a brain, but most of them, in fact all of them, can handle the chaos and complexity of the real world. There are ants out there that only have 20,000 equivalent transistors in their entire body, but a digital watch has over 500,000 transistors on average. Why is it that Mother Nature can do so much with so little? Well, that's exactly the sort of things that I'm trying to find out.
Tilden has gone back to basics. He constructs his robots from the simplest electronic components, with the fewest number of transistors to keep them simple and tough. From old electronic circuits and bits of discarded Walkmans, he can construct a robot from scratch in under an hour. Once powered up, the robot starts to interact with its world without the aid of a programmed digital brain.
Several years ago, we found a method by which we could actually get at creatures that using just 12 transistors or arrays of 12 and 6, we all of a sudden were getting robots that for an equal increase in complexity, we were getting an equal increase in ability.
The breakthrough was the development of the nervous net. Like an animal passing electrical signals through its nerves, the nervous net is a series of signals that pass through transistors in the circuit board to make the robots walk. Different signals can produce different walking techniques. Even though the robots are electrically and mechanically simple, they can climb over and avoid any obstacles.
One of the major advantages of nervous networks is, in fact, the degree of robustness that we've noticed with these devices. And they things survive no matter what sort of damage you do to them. Now compare this against something like a computer brain. If you all of a sudden quaff a beer and you destroy some brain cells, okay, you wake up the next morning and you've got a bit of a aching head, but you're still working. But if you do the same thing to a single transistor in the millions that you find inside a computer, then goodbye, Charlie.
Tilden's robots will work even if their limbs are damaged. In fact, they will keep on going to the bitter end. Tilden believes that this sort of ruggedness will be crucial if robots are to survive in the real world. No one is quite sure where Mark Tilden's nervous nets will lead, but his robots are certainly unique, and he has managed to achieve so much with very limited resources.
It's exactly how biologics work. That is, if you can make machines which essentially don't use computers per segment, but essentially just use the same nervous tissue or equivalent nervous tissue as Mother Nature does, then the future of robots might be very cheap and very biologic indeed.
This is a vision of the future. The Urban Warrior Series 3000 Recon and React robot is capable of operating for months at a time. It has bulletproof Kevlar armor and can track its enemy in the dead of night. Urban Warrior exists only in the imagination, but Robart 3 is for real. It has been built to respond to urban conflict.
Battlefield scenarios are changing, getting more into urban warfare. And the idea here, this is a robot you could take into a scenario like that, send it into a building that may or may not contain snipers or other enemy agents. It would search out the building and leave the humans outside where it's a little safer.
Robart 3 is programmed with sophisticated machine intelligence, so it can learn how to operate in an environment it has never seen before. It's linked to an operator who decides where to search, but Robart 3 makes all the decisions on how to get there. Robart 3 has a companion robot that follows it into a building. It provides a communications link with the operator when Robart 3 goes deep inside. The companion can also detect intruders if they enter a room after Robart 3 has left. And Robart 3 has another trick up its sleeve.
The next obvious step is, okay, you arm this thing and you give it the capability to actually do some damage.
Look on his safe.
Robart 3 is armed with a Gatling gun that can shoot ball bearings or tranquilizer darts.
We want some type of device on there that can deter or delay a detected intruder without actually performing permanent injury or death.
Gun computer 4 is active. There is an object 70 inches direct.
Robart 3 can identify and shoot a target, but the military doesn't want it to be completely independent yet.
There'll be a human involved there, at least initially, to make the determination that this is in fact a valid target before any type of lethal action will be authorized.
Robart is still a laboratory experiment, but there are active killer robots already on patrol. They don't look like the Terminator. They are four-wheel drive vehicles that have been converted into lethal robots. This robotic rifle is capable of firing 240 rounds a minute with pinpoint accuracy. It never tires, it never misses. This is Fire Ant, a mobile tank destroyer. It goes out into the bush and waits for days, months, even years for its prey. When it identifies an enemy tank, it fires with deadly precision. Will modern warfare be fought exclusively by robots?
Looking to the near future, we are going to have technological warfare. We're not very far from it now, but essentially humans removed from the war. There's a lot to be said for doing that, and we're just having one set of robot machines fighting against another set of robot machines.
I don't see a scenario in my lifetime anyway where it's going to become exclusively machine versus machine.
It's nice to think that only the robots will fight with the robots and no one will ever get hurt, and somehow it'll be just like a rather expensive chess game being fought with robots of steel. I can't help but worry that some of that warfare is going to spill over and that there will always be human casualties.
If hunter-killer robots are let loose, will we be able to control them? This very threat prompted science fiction writer Isaac Asimov to create his laws of robotics in the 1950s.
The first law is as follows. A robot may not harm a human being or through inaction allow a human being to come to harm. Number 2, a robot must obey orders given it by qualified personnel. unless those orders violate rule number 1. In other words, a robot can't be ordered to kill a human being. Rule number 3, a robot must protect its own existence. After all, it's an expensive piece of equipment. Unless that violates rules 1 or 2.
But these laws were fiction. Do they work in the real world?
In reality, they're not applicable. Even if you look at some of the military machines of today, a cruise missile, it does not obey Asimov's laws. In fact, it breaks them. So when we look to robots, intelligent robots of the future, I don't think we can look to fictional laws to save us. The robots will be doing things for themselves, and that certainly won't be stopping because they might injure a human.
I wouldn't build any type of autonomous system that I hadn't provided all kinds of safety precautions in there to keep it from doing things that I didn't want it to do. I wouldn't focus strictly on the 3 laws that Asimov put into his literature, but you've got to do that kind of thing or you're going to have trouble on your hands.
Tobor, the most amazing, the most fantastic creation of man's mind.
Oh, he looks alive.
For Tobor can live where no human can breathe, in the airless atmosphere of outer space. Electronic scientists have designed a practical spaceship. Atomic power makes space travel possible, needing only the most valuable of all secret scientific achievements. Space-conquering giants that man can control.
Like Tobor, our real space explorers are robots. Robotic space probes like Voyagers 1 and 2 traveled through our solar system out into the far reaches of the universe. They may not have arms or legs, but they do have fantastic vision systems.
Those types of systems have their place. A rover on the surface provides you close-up analysis of the surrounding terrain. You can actually put a science instrument up against a rock. If you're in the sky, you can't do that.
The first robotic system to land on the moon was Surveyor 3 in 1963. But it wasn't mobile and could only study what its arms could reach.
If you land in one spot and you're immobile, it's kind of take it or leave it, and that's the only thing that you get. I think that most scientists feel that mobility is absolutely essential.
NASA used research from different areas of robotics to develop mobile space rovers.
Rovers provide mobility. We might think of a rover as a mobile instrument platform. The rover is providing the mobility with which the scientific tool can look around and feel and see different sites that it can be exposed to.
The first successful autonomous rover to explore another planet was Sojourner, which explored the surface of Mars in 1997. It investigated the area around the lander and sent back detailed pictures of the Martian surface. This is its successor, Rocky 7. Like Sojourner, it uses wheels. Legs may be the best system on Earth, but for space exploration, they would be too heavy and clumsy.
With legs, you use more energy than with wheels, and for space applications, you want to use as little energy as possible. So not only do we use low-energy electronics on board, we also want to use low-energy forms of mobility.
Wheels are proven technology. Rocky 7 is extremely stable. It has a sophisticated computer brain, and it's designed to explore its way around a planet it has never seen before.
The Sojourner was basically controlled by the lander, so it could not move outside the line of sight of the lander, which means it couldn't go more than about 30 meters distant from the lander. So distance is a major factor. Rocky 7 has the capability for self-location even outside the line of sight of the lander. So it uses landmarks, it uses sun sensing, it uses various approaches to figure out where it is.
Rocky 7 will have to operate for long periods on its own. It's intelligent enough, to explore without direct control from Earth.
All Mars rovers have to be autonomous because the amount of time it takes for a signal to get from Earth to Mars is too long. And so we send it some commands in the morning and then it's on its own all day long. And it has to be autonomous enough to be able to accomplish something meaningful.
After it receives its commands, Rocky 7 can navigate large distances, collect samples, and analyze them by itself.
The purpose is to provide a surrogate for the scientists to be able to do experiments, to be able to view the terrain, send pictures back, place instruments, send science data back. Instead of sending an astronaut, you send the rover.
Despite all its sophistication, Rocky 7 cannot be expected to explore a whole planet.
Planets are vast territories, and we don't explore them by just seeing a little piece. Our traditional view of planetary explorers are that they land, leave the lander, but not very far. They're reliant for computing, for commands, for processing, for viewing, for position estimation on the lander as a mothership.
Red Whitaker has been working on a robot that can travel much further distances. This is Nomad.
Nomad is a new class of planetary explorer, which is self-contained, self-reliant, with the ability to leave the lander and travel afar. It has the ability to perform long-distance, long-duration traverses, measured in hundreds of kilometers, not a few meters, and to operate over months or years, not days or weeks.
Nomad may be the perfect machine to explore the Martian terrain in the future, but it has one main disadvantage: size. Because payloads on board future missions are so limited, NASA is looking for much smaller rovers. This is the Nano Rover. Tiny robots like this may be the future of space robotics. Measuring just 12 inches long, it's going to the surface of an asteroid.
That mission will be to find interesting places that we can take images of, that we can take scientific data. We carry two different spectrometer instruments that will determine the elemental composition and the mineralogical composition of the asteroid.
The unique wheel supports can swivel around if the Nano Rover tips over. On its mission, it will face a more serious problem. An asteroid has almost zero gravity. The designers have decided to use the low gravity to help the robot move around the asteroid. By flicking its legs together, it can jump up and bounce over the surface.
When you go faster than a certain speed in a zero gravity environment, you will take off from the surface. And you can plan that trajectory, much like you plan trajectories for spacecraft. By controlling the speed and understanding how fast you're turning the wheels, you could predict where you're going to land. So literally, I mean flying.
We'll just hop, and we'll use scissors-like motion of the struts to hop the vehicle into the sky as little as a meter or two, and perhaps as much as 100 meters or more.
Other robots are already at work in space. A dexterous robotic arm is an essential tool for astronauts working on the space shuttle. It helps them capture and repair satellites, like the Hubble Space Telescope.
The primary advantage of using a robot in space is to avoid having to have a human go out in space and do extravehicular activity, or EVA as it's called. It's a very dangerous operation. One estimate done about 10 years ago was that there would be a fatality approximately every 1,000 hours of EVA. It's much more safe to have a robot doing things in space than a human.
NASA scientists are developing even more sophisticated robot arms to work on the International Space Station. But the strength of a robotic steel arm can be a hazard.
Because a robot is made of metal and is strong, it can do damage, and this presents a potential safety hazard to manned operations.
To prevent this, The arms have been programmed with machine intelligence that teaches them to avoid getting too close to the space station or the astronauts.
Robot arms and robots in general for space missions will be very important in the future for several reasons. One is they can be stored indefinitely with very little environmental requirements. They don't require food, oxygen, waste disposal.
They're expendable. Should they fail, you don't lose human life. And that's what's very important.
They can operate in environments where humans cannot operate because of radiation, heat, cold.
The fears, of course, are the same as with any science mission, that something will go wrong. As some famous old guy here at JPL once said, you're always one transistor away from failure.
When you reach the Forbidden Planet, you will meet a charming character in the robot, able to produce, on order, 10 tons of lead or a slinky evening gown. Always at your service.
NASA hopes that in the future, robots will help us colonize new worlds and build bases across our galaxy.
I can picture fleets of robots in the sense of colonies doing comprehensive exploration. That is going to happen, and also as precursors to human exploration. I hope that someday we'll have machines which will terraform Mars, take huge sections of the moon and make it basically ready for colonization.
Robots will be able to produce fuels, life support materials like water and oxygen, and to build habitat and power infrastructure before the time of human presence.
In the more distant future, spaceships will travel out to the far reaches of the universe.
All systems activate.
They'll travel for hundreds of years, close to the speed of light. They'll carry intelligent, autonomous robots.
Systems set to boot status.
Once the ship reaches the atmosphere of a new planet, the robots will be activated.
Activate. Systems prepare for disembarkation. Proceed to Sector 7. Unit 62, complete construction of mines Unit 7, radiation shield.
The robots will construct homes and biospheres for future human expeditions. Without robots, it will be impossible for us to explore the universe. Robots may even be our first contact with alien civilizations.
Realistically, the most likely alien form we're going to see is not a little green man or anything that looks like a human, but is a robot, is a machine. Because just as for us, it's best to send robots out into space, so for someone else, another species elsewhere, more than likely they would send robots down here.
Robots have come a long way in the last 50 years. They can move around, and some are learning to think. But how fast are they really evolving?
I've decided that robots are evolving about 10 million times faster than we did. They're currently in their minds roughly as complex as insects. But that's already a large step from where they were 50 years ago. So by mid-century, I think we will have machines that are equal and in fact are superior in most ways.
is Hans Moravec right? Will robots ever control us?
I don't really subscribe to the theory that the robots are going to take over and become smarter than the humans. The fact of the matter now is the most sophisticated robots that we have in existence today fall orders of magnitude short in terms of their capability in comparison to even the most inept human being.
I think in my own mind there is certainly a very real scenario where robots more intelligent than humans will actually be running the Earth. After all, if they're more intelligent than us, why would they want to do what we tell them?
I must say, I do read with some amusement this robots taking over idea. We're finding it just so blooming hard to make a robot pick up a cup.
I don't believe that we will ever see a day when all of a sudden we will have to fear that our toaster basically has plans against us.
I think robots are our children. They will, in time, grow more capable than we are and will eventually replace us. They will inherit the universe from us. And I think this is not a bad thing. I think they will remember us, and they will be able to accomplish far more than we ever could have. So I think the universe will be better off for our having done this and for their coming into existence.